So we'll look into linear regression with Python, and we will try to perform this on a dummy dataset which is already provided in our libraries in Python. Now we will perform this on a very easy and generic dataset of house price prediction on Boston housing dataset. But linear regression is widely used in different organizations, majorly in time series forecasting and financial data prediction. Um, Apart from that, one of the common studies is in marketing, where we want to find out how much budget should be spent for a particular product based on the revenue which we are getting from the advertisement cost, right? And if possible, at the end of this course, I will also showcase you some of the use cases where how Lenskart used linear regression or regression based models to perfectly find how much to spend um, in order to in their advertisement. Initially they were spending 5 crore rupees and the revenue was only 5 crores, so it is not a win-win situation. But after that they performed some analysis, they realigned the entire business model, and with the same 5 crore of advertisement budget they were able to fetch more than 50 crore north of it, right? So we will look into the house price prediction on the Boston housing dataset, and you can think of a scenario where you are a real estate agent and you want to particularly predict the house prices of a particular region in Boston, right? And it would be great if you can make some of the automated system which predict price of a house based on various input, which is known as feature. We have talked about yesterday in the car price prediction model, where the features were mileage, year of registration, right? The brand of the car. So these were the feature. Likewise, we'll have certain features in the Boston housing dataset. Okay, we will be using the supervised machine learning algorithms, right? Because we want to predict the price of the house, and obviously this house price should be available in our data set. Had the price of the data not been present, we could not have used uh, uh, supervised machine learning models like linear regression. We if the label data set or the end predicted value or the actual price of the house was not present, we could have used clustering based model, which we'll look into in the subsequent classes. Now, as we know that linear yeah, I pinged you the drive link, right? Okay, so as you know that linear regression is widely used in the scenario where you have data set which is continuous and you want to predict a continuous data value, right? Like the price of the car or the sales of a car, or the number of products which you are going to sell in the next month or the next year, right? So all this forecasting type of data, which is obviously continuous, can be um, predicted through linear regression. It is a very powerful technique and can be used to understand the factors that influence profitability. It can be used to forecast sales in the coming months by analyzing the sales data for previous months. It can also be used to gain various insights about customer behavior, right? If you want to, predict the customer spending, say for example, every month I spend 12,000 rupees on my household, um, in my household stuffs, right? Like buying groceries, going to the supermarket and buying essential commodities for my home, right? So I spent 12,000, and from there you can take the data from I generally shop from Star Bazaar, so you can go to Star Bazaar and take the historical data of all the customers of Star Bazaar, and from that you can forecast that this guy is going to spend say 13,500 or 14,000 or 15,000 based on what's his income level, like how many people are in the house earning, right? So this all depends on the predictor values. So these are all the features, whether my income or my age or the number of people in my house. All these are the indicators based on which we can find the customer behaviors. Now, linear regression, as we have understood earlier also, linear regression is first, which is statistically very important in the field of finance, investing, and other disciplines, that attempts to determine the strength and character of the relationship between one dependent variable and the other independent variable. As we talked, independent variable is the variable which you want to predict, right? And dependent variables is what you want to predict, and independent variables are the ones which are predictor, and it helps you to predict the dependent variable. Linear regression is a statistical technique where, based on a set of independent variable, a dependent variable is predicted. All clear? I think we have gone through this earlier. Just want to give you a revision. Now, what is a regression? Regression is something where you have a data, you feed the data to a regression model, and it gives you the relationship, right? It gives you the intelligence. It gives you the prediction of what happens with the relationship of X and Y. Okay, how strong the relationship is between X and Y, right? Now, there are some examples which we can particularly look into from a regression point of view. Now, first is the stock price prediction. We can predict the price of a stock, which depends on the dependent variable X. Let's say recent history of stock prices, news events, right? We can have different types of predictor values, like, for example, recent history of stock price, any news event, any related commodities, or for example, if there is a change in the management, right? Stock prices are generally affected by these factors, right? Next is we want to predict, the tweet popularity. We can also estimate number of people will retweet for your tweet in Twitter based on number of followers, popularity of hashtags, right? So we would have some dependent variables like how many followers we have, and how number of followers of your followers, right? Features of the text tweeted, popularity of the hashtags, and number of tweets in the past, or retweets in the past. So you can add as many dependent variables as possible, and you can find out what is the popularity of your tweet. So obviously this will be a number, right? Next is in the real estate, where we will look into the prediction of house prices. Now, as we discussed earlier, we can also predict the house prices and land prices in the real estate. The logic behind is similar. You have some predictor values, and based on that, you will predict the dependent variable, right? Now, regression is of two types. One is the simple linear regression, and the other is the multiple linear regression. Now, simple linear regression is somewhere there is only one, you know, um, independent variable. Okay, that is a very simple linear regression. Let's understand this by an equation: y equals to mx plus c plus error, right? This is a simple linear regression. Why? Because you have only one independent variable. This is your independent variable. And this y is your dependent variable. Right? If I change this to y is equals to m1 x1 plus m2 x2 plus c plus error, it means that you have now two independent variables. And that's when you call it a multiple linear regression. Right? So now you understand what is the difference between a simple linear regression and a multiple linear regression. A simple linear regression will only have one independent variable. A multiple linear regression will have more than one. So you can have 3, 4, 5, 6, 7, not a problem. So it will be a multiple linear regression. Okay, this is the equation. Now, how does it look? So if you have only one independent variable, obviously the graph will look like this. This is your y and this is your x, and the graph will look something like this. But if you have two independent variables, the graph will be probably a 3D graph. Okay, it's difficult to showcase this here, but try to understand that the graph will look something like this. Okay, so in here we will understand what is a gradient descent algorithm, and based on that we will try to understand that gradient descent is a huge topic, and we will cover this gradient descent in one class. Okay, we have different types of gradient descent, and when to use what type of gradient descent is something which we will learn in the near future. Okay, but for now try to understand one thing. So whenever you plot a graph, right, so you have certain data points. Say for example, I have a data point, and based on my analysis, this is the best fit line which I have created. Okay, now someone from our team, say for example Bhargav came and say, sir, I think the best fit line should look like this, right? Another one, say Hari comes to me and say, this is the best fit line. Okay, so we have to understand one thing, that the scenario where the errors are the least, is the best fit line, Now how will you calculate the error? You have to basically find out the difference between the predicted value and the actual value, right? Predicted value and the actual value. And say for example, if my RMSE is, say for example, 2.9, Bhargav's has 2.6, and Hari has, say, 3.2. Okay, then we will consider 2.6 as the best line. Okay, that is the best fit line. Now if you want to draw this, if we have a gradient descent, right, what does gradient descent means? It means that as and when you change the steepness of this line, so for example, initially it was like this, now you change this to this, and as and when the steepness changes, the error value or the RMSE value will also change. And based on that, if we plot this error score here, right, at one time you will get the best value, which will be the least error. So if you plot these errors, or rather this 2.9, 2.6, and 3.2 in this graph, right, it will lie on a curve plane. And the one which is having the best value, right, if it is 2.6, this is our best fit line. And when we draw this gradient descent on a gradient descent plane, the point where the algorithm works the best, right, it is the ideal point, and we will call it global minima. We'll come to this all in the subsequent classes, don't worry about it. Okay, for now try to understand that gradient descent is used to find the best fit line. Now this is actually the goodness of fit. So we try to find out the metric which is the best fit for our algorithm. Now coming to the multiple linear regression. So as I said, multiple linear regression is where you have multiple independent variable or more than one. While you discover the simplest fit line, you will able to adjust a polynomial or regression towards the mean. And these are called the polynomial or regression towards the mean. So don't worry about it. It's the same logic where we were talking about a simple linear regression. Now we have changed to a more complex relationship. Obviously, if there are two, variables or two independent variables in an equation, the relation becomes a little complex, right? As and when you add more variables or new independent variables, it will become more complex, right? So for example, if you want to just predict the house price, you can use only one variable, say square feet, and based on that you can find out the price of the particular house. But now if you add in more details to it, like number of bathrooms, you have number of bedrooms, lot size, and your build, you see the variables are increasing, and based on that our graph will also change. So you will not be able to have only the data on a 2D space. Rather, you should have a hyperplane where all these points will be present. Okay, we'll look into the multiple linear regressions as well. Now, the performance of the model, we have already discussed yesterday that the performance of the model can be, you know, um, calculated using RMSE or MAE, right? Mean absolute error or mean squared error, right? And this is what we have discussed here also, that this is the plot where you have all of your data point, and this is the best fit line or the predicted value. From here you will find the difference whether it's negative or positive, and based on that you will calculate your root mean square error or mean absolute error or whatever it is, right? Now one question is, how do we determine the best fit line? As I said that we have multiple lines, which one is the best, whose is the best? And for that we have to understand that the line for which the error between the predicted value and the observed value is minimum is called the best fit line, right? The error is minimum for Bhargav, so this is the best fit line. Okay, these errors are also called residuals. These residuals can be visualized by vertical lines from the observed data value to the regression line. We all know now that the residual is the difference between, this is exactly the residual, right? The difference between the predicted value and the observed value. Okay. Now coming to the most important part, right? Yesterday, someone asked me what is a bias, and I, purposely didn't go further with the definitions because it might be a little tricky to, um, get inside that topic and living without, spending 15 to 20 minutes. So to answer that, I will quickly erase this, or rather, okay, I will quickly erase this.
There was option called quick clear canvas in the last.
Yes, that's fine with this. Okay, thank you. Yeah, so what is a bias? Bias is something, if you just want to understand from a definition point of view, bias is the inability for a machine learning model to capture the true relationship between data points. Say, for example, you have points like this, right? And for example, let's take a example of height and age, height and weight. Say, for example, height and weight. So we have height and we have weight, right? We all know that, as in when the height increases, the weight also increases because you have more bone density. And this is just a sample. Okay, don't try to relate it with any um any particular, natural scenario, and we can get into an argument. But just try to understand that there is the plot of, height and weight of of an animal. Okay, right? Now you can do one thing. If I want you to ask, if I ask you to, plot a line which basically defines this relationship, you will ideally plot a line like this, right? Ideally, okay, not linear regression. An ideal scenario would be you will plot a curved line like this. Okay, this curved line basically tells you the exact, relationship between the height and the weight. That as and when height increases, the weight will increase, and after a certain point, it will be, somewhat standard. Okay, and now if I ideally ask you to plot the same, if you have the same data point here, and if I ideally ask you to, plot a linear regression, what you'll do, instead of a curved line, you will draw a straight line, right? You will draw a straight line. Now, because the straight line can be curved, right? Can be curved like a true relationship. This is your true relationship. This is your true relationship. And this is your linear relationship. This is your linear relation, right? It has a relatively large amount of bias. So this means that this linear line is not able to, uh, actually get into all these data points. Okay, so there is a high bias. There is a high bias. Now, when will you say that the bias is low? So if you have points like this, right? This is the same point. All three are the same points. Okay, pardon me for the figure. Okay, so if you have, ideal bias, your ideal, this is your ideal relation, and it should pass through all the points, right? It should pass through all the points. Now this line, if I you know if I just want to say this has a low bias, this has a low bias. Why this is low bias? Because it goes through all the points. There is no bias to any of the points, right? But this relationship has a high bias because it ideally passes through, a one straight line, and this line has certain, this point has certain residual, this has some residual, and so on. So all these residuals collectively make a high bias. Okay, this makes a high bias. And if I calculate the sum of square, ideally this sum of square, see if this sum of square is 4.9. Okay, suppose this will be ideally 0. Why? Because there is no difference between the data point and the line, right? There is no difference. So you can see the bias is very low. The bias is very low. Now, just try to understand that if I have 100 data points, okay, if I have 100 data points and I have divided this into say 70 and 30, and this 70 is what I have plotted here. Okay, this 70 is what I have plotted here, and this 70 is what I have plotted here. Now, when you try to create the same relationship, so this is called the training data set. This is called a training data set, and this 30 will be testing. And you try to draw the same, line with this testing data of 30, your ideal relation will look like this. Okay, so the linear relation won't have, much difference. It would ideally be, say, for example, 4.7 or 5.2, right? Or 4.5. So there won't be much difference. But if you try to plot the same thing with the same equation, say for example, if I plot this 30 points, right? And if you have the same figure, see, there are certain points which are very far away, right? There are certain points which are very far away. Some are matching and some are not at all matching. So this means this sum will ideally be, say, for example, 3.2. So the difference you can see, right? The difference is from 0 to 3.2. And here the difference is only 4.9 to 4.7. So it is zero point 0.2 or 0.5 or zero point 0.6. But the difference here is 3.2, which is to the larger extent. And this is what we call that bias. So bias is something where it works very well with the training data set, right? It works very well with the training data set, but it fails terribly with the testing data set. And this scenario is also called overfitting. This scenario is also called overfitting. Don't worry, we'll come to this again. Okay, it's just a rough. I'm trying to make you understand. This scenario is called the overfitting. So in the training data set, you have a very low bias, but it fails miserably when you test it. Okay, so this is the bias. Now we'll come to something called a the variance. Now variance will refer to the amount by which the predictions would change if we fit the model to a different training data set, right? Now, for example, the same data. Okay. Now, as I said, variance, right? Variance is actually the amount in which the predictions would change if we fit the model to a different training data set. So this was our one training data set where, we had split it to 70-30, right? If we have another data set, say for example, 120, and we say, for example, split it to 84 and 36, 84-36. Okay. And when we train this and we test this and train this with the same model here, this will be hugely different. Okay. Now the line which we have drawn here has a very high variability. So this has a very high variance, right? So whenever you have an overfit model, you have a low bias and a high variance, right? And for that matter, your sum of square which will create, right, will also be very different. It will be very different. So if your sum of square is 3.2 here, it will say 7.9 or 9.6 or 10.2. But in here, when we have a linear relation, right, the sum of square will be not much different, say 5.6 or 4.3, right? So it will have a certain, it will be nearer to the previous sum of squares. So it's very difficult to, predict that how this particular model might perform. It might perform good at times, like if you have a data set like this, but it will perform very bad, majority of the times. Yes, I will repeat this in short. So this is what the bias and the variance is. Now, if we try to find a relationship, so what it does say is that in contrast, the straight line which we have here, the straight line has relatively high bias. It has a relatively high bias, but it has very low variance. It has a very low variance. It has a very low variance. Why it has a very low variance? Because the sum of square is relatively, same. is relatively same. Okay, and this is what we call overfitting. As I told you, this is your overfitting model. It fits all the data points. So this is the overfitting model. We'll come to something called a underfitting model as well. Now, in an ideal scenario, okay, in an ideal machine learning scenario, you should have, a low bias and a high, sorry, should have a low bias and a low variance. Okay, this is your ideal model. This is your ideal model, right? This is your ideal model. So in a machine learning model, the ideal model has a low bias and can accurately model the true relationship. It will be able to model the true relationship ideally. Okay, obviously you cannot get the best line, but rather you will get or the true line, but rather you will get the best line. Okay, and for that you should have a low bias and a low variance. Why we want to have a low bias and low variance? Because we want to produce consistent predictions across different data sets, right? For example, if you have created a model which works very well with your data, right? But if someone uses a different test data set, it fails miserably. So your model is not with low bias and low variance. Understood? And this can ideally be found using a sweet spot. You should ideally have a trade-off. So you have to find a sweet spot between a simple model and a complex model, right? So this is our very simple model and this is a very complex model, right? So you have to find a sweet spot, which we'll talk about in the bias variance trade-off. Now, how to find this, sweet spot? We will find this sweet spot using regularization. We'll find this using regularization. We have a separate class for regularization where we'll look into something called L1 and L2 regularization, which is also called, ridge and lasso regularization. Okay, and we will also look into, so this is for our linear regression, and we will look when we go down to classification, we will look into something called the boosting and bagging. Bagging is something which we'll learn in the random forest class. Okay, so I will so in simple words, if you have same type of data set, say for example, I have only these few data set, so you can have a simple model, right, or a complex model. A simple model is where you have a best fit line, right? You have a best fit line, and a complex model is where you are fitting all the points, right? So this squishy line is called a overfitting scenario. This is a overfitting. Now in overfitting, what happens is you have a low bias and a high variance, right? And for a simple model, right, you have a high bias and a low variance, and both of them are not ideal. They are not ideal, right? To make an ideal scenario, what you have to create, you have to create a model which will have a low bias and a low variance. How to check the variance, right? Variance is nothing but if you have different data sets. Say for example, I have data set 1, data set 2, data set 3, data set 4. Okay, and you test, say, the error. So in dataset 1, your error is 2.5. In dataset 2, you have 2.6, 2.51, and 2.62. So you have very little variance, right? The you know the difference between these data sets are very different, is very low. So that is when you call it as a low variance. But for example, if you take inside this D1, right? In this D1, you have splitted the data set into two parts, say 70 and 30. If you have total 100 data points. Now, if you have divided this into 70 and 30, the squared error in the training, this is your training, and this is your testing. In training, you have a squared error of say 2.9, but in testing, if it is 7.2, you see a huge difference between your error values. So this tells this you have a very high bias. Understood? It has a very high bias, and we will understand this through numericals in Python, okay, which will give you the exact picture. Okay. What is a validation data set? See, for now, try to understand that we will divide our data into two parts. One is training, okay, one is training, and one is testing. Okay, for now, try to understand there are only two parts. We will come to scenarios where we will divide this data into three parts, where we have the validation data set as well. For now, let's not confuse other guys, and we'll make sure that we are taking only two parts into consideration, the training and the testing. Okay, it might be a little difficult for others to absorb, but when I will come to, is it good to calculate RMSE by MAE for training dataset? Isn't something we are getting from R square? Yes, yes. That is something which we will look into when we will have a performance metric of a regression problem. Okay, but for now, this is just for your understanding. Okay, because if I try to do more, calculation here, it might be a little difficult for others to digest. Okay. Because I know there are 2-3 folks who come from a non-technical background, so I don't want to mix things up. Okay, so the main challenge which we talked about is overfitting and underfitting, right? When you have an overfitting scenario, you have a low bias and a high variance, and vice versa. When you have an underfitting scenario, you have a high bias and a low variance. Okay, you want to make sure that you have an ideal relationship, and for that, an ideal linear regression would be, or ideal model will be when you have a low bias and a low variance. Okay, now how to achieve this? This is called the bias and variance trade-off. Now, bias are the simplifying assumption made by a model to make the target function easier to learn. Variance is the amount that the estimate of the target function will change if different training data is used or was used. The goal of any supervised machine learning algorithm is to achieve low bias and low variance. In turn, the algorithm should achieve good prediction performance. Right? Now, if you have a bias line is, now if I want to plot this over say model complexity, we all know that as the model complexity increases, when I say model complexity, it means it tries to fit all the data points. It tries to fit all the data points here. See, it tries to fit all the data points. This is a complex model. So as and when the complexity of the model increases, right, you see the bias line will also go down. And as and when the model complexity increases, the variance will keep on increasing. And from here, we find a balance, which is the sweet spot, right? We call the sweet spot. And in here, we are calculating the mean squared error using the bias square plus variance. We'll come to this when we'll do the calculation. Okay, and it's very difficult to find the perfect sweet spot, and we will come to a gradient descent scenario where we find the global minima, and from there we will try to find out the sweet spot. Okay, for now, try to understand what is the bias variance trade-off. It is actually finding the sweet spot where we have the ideal low bias and ideal low variance. Okay, now error versus amount of data. So we have to understand one thing, that the more the data is, okay, the less the error will be, because we will be able to train the data with more and more data points. So as and when your data point increases, a time will come when the error will be uh, ideal. And we'll come to this with our Python coding. To perform linear regression, we will be using scikit-learn, right? This is used for machine learning in Python. It is very simple and efficient tool. It can be accessible to anyone, so you don't have to worry about any licensing. And it is open source, and it is built on top of NumPy, SciPy, and Matplotlib. So you will be able to do a lot of functions which we can already do in NumPy, SciPy, and Matplotlib. Okay, so with scikit-learn, you can do any sort of algorithms. This is the cheat sheet. So you can either do your regression problem, you can do your dimensionality reduction, you can do your clustering, you can do your classification. Okay. Now, as I said, we will be discussing about training and testing splitting, right? So train and test is something which we will understand in our data, right? And with the testing data set, we will divide it into two parts, which is validation and testing. Now, what happens is, when you have, say, 100 data points, you basically divide it into two parts. One is the training and one is the testing. And within that testing, we will further divide it into two parts, which is one part we will assign to validation, right? So we will train the model on top of our training data set. Okay, for example, we will train the data or model with 60 data points. And with that 60 data points, we will train the model, we will create a model, and with the validation data set, which is the 15 data points we have, we will perform some parameter tuning just to make sure that the model is robust enough. Okay, and once that parameter tuning is done, we will move on to testing the model. We will compare the test to prediction, testing the target to the accuracy. Okay, and we will make predictions on the testing data set. So this is just a simple diagram which I wanted to show you. Now we'll start with the coding. So I will request you all to start with running the script. Okay, please open your repeater notebook. If it is already open, just give me a confirmation. Okay, great. So I will start with running the script. So what I have done, I have basically installed all the libraries which are required, or the packages which are required. Okay, importing some of our packages: NumPy, Pandas, Seaborn, and Matplotlib. This is my go library. And from here, we will use the sklearn library to look into data set, right? If you remember, we have used some of the data sets in previous class to perform statistics. Like in Seaborn, we have looked into data sets like the tip data set. Likewise, we have some data set in sklearn. We will use the load Boston. Load Boston is a data set which basically has the data for predicting the house prices in Boston area. Then we will import model selection train test split. In order to perform this split, right? In order to perform this split, we will import sklearn.model selection import train test split. And then sklearn.linear model import linear regression. Okay, because we'll be using linear regression here. From sklearn.metrics, we will import mean absolute error and mean squared error. Okay, we will import mean absolute error and mean squared error. Let's run it. Right, and now we will load the data in the variable Boston, and let's look into some of the keys. So what we have a data, we have target, we have the feature names, right, description and file name. Okay, let's print this description column to understand the data. So you have these attributes, which is CRIM, this is your column name. Okay, you have total 506 data points. CRIM says per capita crime rate by town. Obviously, if you want to, buy an apartment, you want to make sure that there is no mugging, there is no crime in that area, right? Then you have ZN, the proportion of residential land zoned for lots over 25,000 square feet. So this basically gives you the residential land, right? How much residential land or proportion of the residential land is present there. Next is industrial area, proportion of non-retail business acres per town. Okay, just to make sure that how much industrial area is there. Next is there is one river which is Charles River dummy variable. If track bounds the river otherwise. Okay, so just to make sure that if there are rivers in that area. Nitric oxide. So these are some parameters which people consider while buying house. You have average number of rooms per dwelling, right? RM, proportion of owner occupied units built prior to 1940. Okay, weighted distance to 5 Boston employment centers, index of accessibility to radial highways, and so on. So you have these type of data. Obviously, when we look out for data or to buy a apartment, we basically look out for what is the real how many nearby schools are there, how many nearby hospitals are there, different shopping malls, how well it is connected to the metro, and based on that we decide what should be the ideal price of that particular apartment. Now if we look into the features, these are all the features we had, right? And in total we have 13 features. And if I want to specifically look into the target variable, I have target variable which says 24, 21.6 and 34.7, and this will basically be my data set, okay, of the target price of that particular area. It might be 24 million or 21.6 million and so on. So in total you have 506 data points with 13 columns, and let's look into this data. So I have just printed the head. The head will give you 5 data points. Okay, at times in MCQ they will ask you data.head will print how many values. Okay, so you have to write 5. Data.tail, just to make sure that the last value, the last 5 values. Okay, just 5 sample random sample values are printed using data.sample5. So this is what I am doing through EDA, exploratory data analysis. Don't want to take a separate class for EDA because it makes no sense to go through different data set and waste our time. Right? Rather we will understand this with a business scenario. Now we will create a column called data and then price and load the target value to this data set. So I am loading Boston.target to a new column called price. So already you have 13 columns, right? I am just adding one more column. And for that, what you will do, you will just create a column name price is equals to Boston.target. And when you print this, you can see the difference between these two columns, these two tables, right? You have a new column called price, which got created. Now we'll look into this, the descriptive statistics using the describe function, right? What is the count, if there are any missing values, what is the mean of all these. So for example, if I can say that 22.53 million is the cost of mean cost of the apartments. Okay, the standard deviation is somewhere around 9.19. Minimum cost of the apartment is 5, and you have your 25 percentiles, 50 percentile, 75 percentile, and the maximum value is 50 million. Okay, so these are, you can print the info just to make sure if there are any non-null values. So all of them has some values, so you don't have to perform any type of cleaning for now. Okay, data dot is null dot sum. This will give you if there are any null values in any of these columns. Say for example, if there would have been no data here, sorry, no data here, then in that case this column indus would show you 1, right? It will show you 1 here. Next we'll move into the exploratory data analysis. What we'll do, we'll try to create a pair plot, right? What does this pair plot means? It means that all these 13 variables, right, 13 or 14 variables will we will plot one against each other. Okay, CRIM will plot with ZN, and ZN will plot with Indus, and so on. So we will have these pair plots. Okay, it is taking some time, and
I think we need to do show.
yeah. So it will get generated, and yes, it is generated now, but this is too much information. And if I want to create a subset of it, or rather I don't want to analyze all of them together, but for now try to understand with plot is that some of them are highly correlated, okay, either negatively or positively. We'll look into it in the later half. For now we will try to plot this with rows 2 and column 7. So it will basically fetch your data from column number 2 up until column number 7 and create the plots for you or subplots for you. Okay, you can see there are 2 columns and 2 rows and 7 columns. So this gives us a better picture. Now we will be able to analyze this data. Yes, we can do that. Not a problem. Thanks, Bhargav. You can use matplotlib inline just to show the data or plot the data in line. Not a problem. Yeah. Thanks, Bhargav. If you want to, showcase the result in line without using the plot.show every time, you can use the matplotlib inline function. Okay, so now it is little difficult to understand, if there is any relation between the data using a pair plot. Obviously, you can do that. That's not a problem. But ideally, we will create something called the correlation graph. Okay, If we create a correlation graph, it will give you a correlation that, okay, CRIM and CRIM, obviously it will have a one correlation. But CRIM with ZM is, minus 0.200469 and so on. ZN has with Indus minus 0.533828. And this is how it is. Now, to go through each and every data point, it's a little difficult. Rather we can create a heat map. Right? From the heat map, we'll try to understand that whenever there is a strong relationship, whether it's positive or negative, it will be in dark. See, a very negatively correlated data is with Indus, right, and Zn, because it has a correlation more than 0.5. Is it possible to do correlation for categorical data? It is possible, but I don't think it will make any sense for us. At times it will make. That's something which we have to look into, what type of data set we have. But correlation, obviously we can find the correlation if we can do one hot encoding, and from there we can find any correlation between the data of different categories. So you have to basically divide the categories into different parts by doing a one hot encoding, or any encoding technique, and from that encoding you have to find the relationship, if there is any relationship. We'll come to that in the classification classes. Okay. Now, wherever it is dark, you can see the correlation is high. Say for example, 0.7 minus 0.75. It says that the correlation is very high. If it is negatively correlated, and we'll look into it how we can find the important features based on the data. Okay. Now I am not doing any type of feature selection here. I'm just showing you a plain EDA of the process. We have many such examples where we'll do all sort of feature extraction, feature processing. You will also see one example in the slide which I have shared. If you want to code this along, you can do that. I will, or else I will share the notebook with you. Next is the train, test, split, and model training. Right. So what you will do first is try to since I already included the price variable in the data, and if I want to train the data, I want to make sure that the price is in a different column. So in X, I have all my independent variables. See, these are all independent variables. Okay. And in Y, I have the dependent variable. So now you can understand Y equals to mx plus c. So Y, this is your Y, which is dependent. M, which will calculate, or the algorithm will calculate. X is your independent variables. Okay. And now from here, what we'll do, we will create a train test split. Okay. To train test split, we have X train, X test, Y train, and Y test. Okay. How this works. So right, if you have 100 data points, you are basically dividing this into two parts. Right. Say when in this code, we are passing a test size of 0.2. It means that 20% of the data will be with testing and 80% will be for training. So this is your training and this is your testing. Okay, so you are creating a X train, your X test, Y train, and Y test using train test split. Right. And if I run this, what you're getting is you have a training data set, right, with 404 values. You have your test shape, right? You have your test, which is 13. So your training has 404 and 13, and your testing has 102 and 13. Okay. Now, from here, we will try to fit this in a linear regression model. So we have already imported a linear regression model. So we will perform linear regression and will put this value inside a variable called model. And in this model, we'll try to fit the X train and the Y train. We are trying to fit the X train and the Y train. Okay. Now, once the model is trained, we want to train this or test this or predict this with the X test value. Okay. We want to test this with the X test value. And once we run, we fill this value inside Y predicted. Okay. And in Y predicted, if we showcase you the result, all the prediction value are present here. Okay. All the prediction value of the data points are present here. Now, next comes the evaluation of the regression model. Now, I have went very fast here just to make sure that you understand it very well. What you are doing is you are basically training the model with 80% of your data and testing it with your 20%. So once I am training it, a model is getting created. Okay, a model is getting created, and once you test it, you have the results, which is the Y predicted value. This is your Y predicted value. And based on that, we will find out if there is a difference between the predicted value and the actual value. If there is any, difference between the predicted and the observed value, we will look into the results. Okay. Just want to show you one more time that we are splitting the data with 80 and 20. Okay, with a test size of 0.2. So the train size will obviously be 0.8. Okay, basis that we have created our train, we have created our test. Okay, we have created our train and we have created our test. Okay, and we fit this model using the linear regression function. Okay, we are fitting this with X train and Y train. From there, we are trying to predict the X test, whatever was left in the X test. And from that X test, we got our Y predicted value. Okay, we got our Y predicted value. Now coming to the evaluation of the model performance. Now, as we have seen in the last class, we understood there is something called the R square value. And R square value is basically 1 minus SST by SSR. Okay, I'm reading this aloud so that we can all understand. It is difficult to measure the quality of a given model without quantifying its performance over training and testing. Obviously, if I give you this type of result, you will not be able to understand what is actually the result is, if there is any significant problem with the model, or whether it is able to test it, right? This is typically done using some type of performance metric, where it is through calculating some type of error. So now we have to calculate the error. We all know that the error is the difference between the observed and the predicted value, right? So this is what the model will do, or we will do through the sklearn model library. The goodness of fit or some other useful metrics for this project will be to calculate the coefficient of determination. So the R square value which we learned in the last class is your coefficient of determination. Okay, this is called the coefficient of determination. R square is your coefficient of determination. R square to quantify your model's performance. Okay, we will learn about different performance metrics. We have accuracy, we have F1 score in classification. Likewise, we have coefficient of determination in regression. The coefficient of determination for a model is useful statistic in regression analysis, as it often describes how good that model is at making predictions. So it will tell you how good the model is in making predictions. Obviously, we understood one thing in the last class, right? In the last class, we understood that if the R square value or the coefficient of determination is 0.81, right? It means that, the relationship between X and Y, in our case, it is going to be multiple X, right? X1, X2, X3, multiple X. The relationship between X and Y, how strong it is governed by 0.81. So obviously, if you have, R square, which is say 0.81, and if you have R square, which is say 0.69, there is a significant difference. So 0.81 have a strong relation, shows a strong relationship between X and Y. And 0.69 shows a not so strong relationship between X and Y. Okay, now R square ranges from 0 to 1, which captures the percentage of squared correlation between the predicted and the actual value of the target variable. As I told you, it will show you the relation or the correlation between the X and the Y, the independent and the dependent variables. Okay. A model with an R square of 0 always fails to predict the target variable, whereas a model with R square of 1 perfectly predicts the target variable. Okay, as we know, if you have, R square equals to 1, obviously it might be a very bad scenario where you are able to fit all the data and without any error. So ideally, it should not be 1. It should be between 0 and 1. Any value between 0 and 1 indicates what percentage of the target variable using this model can be explained by this feature. A model can be given a negative R square as well. How R square formula framed here? Okay, we'll look into the R square formula, how it is framed. In the last class also, we talked about R square. We will talk about R square in detail here. Okay, so one thing to understand before we go to the calculation of R square is that R square can also be negative. Okay, but it indicates that, the model is no better than one that naively predicts the mean of the target variable. So for example, if you have certain data point, you have certain data point that 10, 20, 30, 40, right? And if you sum them up, you have 30, you have 100, right? 100 divided by 4 is 25. So the mean is 25, right? So if this is what the attendance of the class is, okay, in 4 consecutive days, and if I ask you, what is going to be the attendance of the 5th day, you can naively say that, sir, the attendance is going to be 25. And I will say how? You'll say I just took the mean of the 4 values, previous 4 values. So this is a very naive way of saying, right? If you have a R square, which is negative, it means that this model is even worse than, predicting with something called a mean. It is worse than the mean also. So it is that bad. Because if you take a mean, it will probably give you some R values of say 0.1 or 0.25 or 0.3, whatever it is. But if you have a negative value, it means that you are not even able to, predict the model. And it is very, it is worse than very naive models like mean, calculating just the mean. Okay, just go through whatever I have written here, that a model can have a negative R square as well, which indicates that the model is no better than one that naively predicts the mean of the target variable. Got it? Now for the performance metric function in the code, we will look into something called the SST and SSR. We will look into something called the SST and SSR. We also know something called the SSE. In the last class, we have talked about what is the total sum of squares and the total sum of squares of residual. Right? So if you want to look into the Someone asked me how the R square formula is framed here. So in the last class, I discussed something called the right. So you have SSR, you have SSE and SST. Okay. What is SSR? SSR is the difference between the mean, right? The mean, if these are your points in blue dots, the mean line will pass on here. Okay. The difference between the predicted value or the point in the prediction, okay, and the mean value is called the SSR. Is called the SSR, sum of squared of residual. This is your residual from the mean. Okay. And next is your SSE. SSE is basically the sum of squared of error, right? This is your actual data point and the difference between the predicted and the observed value, this is your SSE, right? And from here, we are calculating SST, which is the sum of SSE and SSR, which is your SST, right? Or in other words, you can say SST is your difference between your YI and your Y mean. Okay, the difference between your Y, if you YI, right? And if this is your Y mean, so the difference between YI and your Y mean, this is your SST. And from here we can derive what is the R square. R square is actually the ratio of SSR by SST. Okay, your SSR and your SST. This is your R square, or in other words, you can write 1 minus SSC by SST. So this is how the R square value is framed. It basically tells us the variability or the difference in Y variable explained by the difference in the X variable. How different, how correlated X and Y are. Okay, this is called the coefficient of determination. Coefficient of determination, right? Now, if I go back to the slide, as I said, R square is 1 minus SST by SSR. Okay. Now with R square, when I say the errors should be similar, R square score should be close to 0. So whenever you have a R square value which is closer to 0, it is a bad model. And when you say it is good model, you can say the mean squared error of the linear regression model should be a lot smaller than the mean squared error of the simplified model. Okay, and in that case, R square value should be closer to 1. Now, in the previous class, we have gone through what is mean absolute error, MAE, what is mean squared error, MSE, and we have root mean squared error, right? If someone has any problem, they can go through this slide. I've calculated them one by one, the mean squared error, the root mean squared error, and the mean absolute error as well, right? For example, if you have a data set like this, where this is your quarterly sales and this is what was predicted. So the difference between the observed value and the predicted value is this, right? This is your mean absolute error, which is basically the mod value of, say for example, 50 minus 70 mod. This will give you 12, right? And this is your mean squared error. You have squaring the value. So minus 12 square is 144, 125, 144, and so on. And then you calculate your means, and if you sum them out, you have your mean absolute error. If you sum them out, you have a mean squared error. And if you perform a root under of this value, root under of this, you'll get a root mean squared error. Right? And this is how you calculate these values. Okay. Nothing. I just want to make sure that all of them are together. How to interpret root mean squared error or mean absolute error in simple term, or let's suppose we have to explain them to business side of person. Okay, no problem. So as I have told you, what is a root mean squared error? Root mean squared error is basically a metric which tells you, how the data points are spread. If there are outliers in your data, right? If you have high, variability in the data, you will have a root mean square which is much different from your mean absolute error. So that is one definition which you can give to your business, that the data which we have in our sample set, or or for our hypothesis, is somewhat, having outliers, or they are having a uh, having some variance in the data, right? This is what you can explain, but actually you will be able to explain through, the metrics which you have. Okay, now that we have the regression evaluation matrix, I will quickly take a short break, and then we will regroup again to, look into the metrics of linear regression, followed by a quiz. Okay. Okay, let's suppose we have RMSE of 45 and MAE of 30. How can you explain to business stakeholder what this number denotes? Now, if I just show you this slide, can you tell me what is the difference which you can see here? And I will also show you this, this slide. Right? If you see this slide, what it says is there is no, major outlier in the data. When I say outlier, a major one. Rather, in this, if there was a point of 100 or 200, or some 5 or 6 points with like 40, 50, and 90, 120, in that case, the result would have been very different, right? Your mean absolute error is 10. Your root mean square error is 11.45. The reason why we have this root mean squared error, because it is quite similar to your mean absolute error, the uh, the unit, right? If you have centimeter, both of them will be in centimeter, right? If it is fit, both of them will be in fit. So mean absolute error and root mean squared error has the same unit, but the only difference is that if the difference between mean absolute error and root mean squared error is quite significant, okay, if I say 10 as mean absolute error and 19.5 as mean root mean squared error, it means that there are some data points here, okay, which are very far away from the observed value, or the predicted value are very far away from the observed value. This is an instance of outlier. So the question which you have asked is, if I have a mean squared error of 30 and root mean square error of 45, it means that there are certain points which are, very far away from the predicted value, and it can be treated as outlier. And if that is the case, what you need to do is you need to refine your data in such a way that you minimize the number of outliers, and based on that you will find that the mean absolute error and the root mean squared error both are, very close or nearby. Okay, this is the only instance in which you can tell your stakeholder that, see, my mean absolute error and my root mean squared error are not having much significant difference. That means I have, performed all sort of, outlier analysis.
Yeah, Alankar, remind this side. So
Mhm.
basically, my question is basically, let's suppose my RMSE is 45, or let's
Mhm.
suppose MA is 30. So if my MA is 30, can I say that each observation or each predicted value is having difference of 30 on average? Is it right between the
Yes,
actual?
yes, you can say that.
Yeah, that kind of explanation I was looking for RMSE. So how we
Yes.
can, not the difference. I understood that obviously if there is outlier and if we are taking the difference and we are squaring it up, Then
Right.
obviously it RMSE will be higher as compared to ME.
Right. So when you say the difference, you have to say the absolute difference. Okay, because
Mhm.
if you know sum all the residuals, so if you sum all the residuals which are present in this slide, right,
Yeah.
this will be 0.
Mhm.
Okay, but when you find the modulus of it and when you sum them up, you will probably get 100 here.
Yeah.
Right.
So it means
Yeah.
on average, my prediction is deviating by this much from the actual, right, for the ME. But
Yes, that's right.
for RMSE, how we can interpret in the same line?
RMSE means that your data points, right,
Mhm.
are distributed with a mean average of
Mhm.
11.45,
Okay.
are with a mean average of 11.45 after penalizing the outliers.
Okay. So can we say that this RMSE is basically standard deviation of the error terms, if you have to say?
Standard deviation, yes, you can say that.
Mm.
You can say that. Yeah.
All right. Because sometime uh, we got this metrics, but to interpret or explain to the business side, right, is really difficult, and they are
That's
not
right.
from the analytical side and the technical side, right? So, yes.
Yeah, and believe me, that is the main challenge we are also facing in
Mm.
our day-to-day life. So it's very
Yes.
difficult to convince them with our results.
Yeah. Because obviously it's for specifically organization side, they will look
Right.
for revenue and all, right? So how much, what the revenue we are making. So,
Right. That's right. So it is very important to discuss this type of results in any time series
mm,
analysis, or whenever you do a linear relationship between two variables or three variables.
right. Okay. Thank you. Yeah.
Okay. Yeah. Please use the chat window to get into. Okay. Okay. Only three guys. Come on. We have six participants. And to all, don't freak out with the examples which we are seeing now. It is just for your exploratory data analysis. It's not that we predicting the house price right now, but I just want to go through all the metrics which are present, the R square, um, how to create different type of plots, how to create a regression plot. Okay, rather than just jumping into the conclusion, I want to go through the journey. Let's do some of the problems together from the EDA part of point of view, and then we will move on to actual scenario where we will predict the house prices and will predict some of the metrics or the target variables. Okay. Okay, I am waiting for two more guys. Please join. I'm pasting the link again. Okay, we shall start now. Linear regression is a supervised machine learning algorithm. Very easy. True. Yes, linear regression is a supervised machine learning algorithm. Moving on to the next one. Which of the following methods do we use to find the best fit line for data in linear regression? Least square error. Okay, we use the least square error. Obviously, we have gone through the intuition behind it, that why least square error is used to find the best fit line. Maximum likelihood, no, it is not the answer. Which of the following evaluation metrics can be used to evaluate a model while modeling a continuous output variable? Continuous output variable. Mean squared error, right? Continuous output variable is for regression problem. So we will be using mean squared error. True or false? Linear regression is mainly used for regression. True, right? Linear regression is obviously used for regression. It can also be used in classification problem. We'll go to that when we understand CART. Okay, but it doesn't make any sense. Question number 5. Predictors that are not significant in a regression model can be found using R square, adjusted R square, or residuals. Ooh. Predictors that are not significant is in a regression model can be found using a adjusted R square, right? We have learned this in the last class, right? If I go to right here, you can see that the predictors which are not impactful can be actually found using the adjusted R square values. Okay. That's the end, and we'll quickly move on to our linear regression metrics. So in this particular Jupyter notebook, I'm not trying to predict, the house prices. Rather, I'm just going through the EDA. We will obviously do a lot more problems in linear regression. As I told you, it is actually the basics of your neural networks as well. It is very much important to understand linear regression. At times, there are some terminologies you will find a little confusing, but over the time, we will talk about it again and again, and we will share a document with you where you can go through all of them and understand what actually linear regression is, and what type of questions can be asked to you, what are the different scenarios in which you can use linear regression, any use cases. We will solve some of the problems together, right, in the class. So don't worry about any of the things. Even if you are not able to follow, you know just follow along, ask question. We'll try to answer as much as possible, and if required we can also talk through over call or over WhatsApp. Not a problem. Now coming to the evaluation metric, as I told you, there are three types of evaluation metrics: mean absolute error, mean squared error, and root mean squared error. Mean absolute error is the easiest to understand because it is the average error, just taking the average. Then you have mean squared error, which is popular because it punishes the larger errors, which tends to be useful in the real world, right? And root mean square error is just to, interpret the data in the same unit as the original model or the original unit. Okay. Now, if you want to find the root mean square error, you have to basically import the R square score, right? R square score. From here, we will find the R square value of the model. So what the model which we have created, you can see the predicted R square is 0.59, right? It is 0.59. And when we test this over, mean absolute error, the mean absolute error is coming to be 3.884. Mean square error is obviously greater than mean absolute error, which is 33.48, and mean squared error, right? Root mean squared error is coming to be 5.78. So you can see the difference, 3.8 and 5.78. So it means that there are some outliers in the data, not much significant or rather significant, but just as the mean absolute error and the root mean squared error are different, we are able to figure out that, due to the variability of the data, right? Or rather we can say, since the data are spread in an uneven way, there is a difference between the MAE and the mean squared error, root mean squared error. Okay, just want to you to calculate it. Don't infer anything right now. We'll do an end-to-end project where we'll infer from the top to the end. Don't worry about it. Now I just want to print the data wherein you can see that I have 506 rows. This is the original data which we had. I want to showcase how the true value and the predicted value are different. Okay, just to make sure that with the test data, right, when we have predicted something, so when we predicted something, we have in orange, and the true value or the observed value, right, it is in blue. So you can obviously see what we have predicted and what is the observed value. So there is a significant difference, but again there are some points which are not so significant. So that is how the prediction is also done, right? And it will govern what type of accuracy you have. Okay, just to showcase these results. Now if you want to plot this learning curve, just want to show you that as and when the number of data increases, okay, as and when the number of data increases, the score will also increase. Okay, because with the number of training examples, your model will learn more about the data and it will give you better scores. Okay, for that what we can do, we can shuffle the data. Okay, and we have imported something called the learning curve and the shuffle split. So it will split the data and shuffle it. Okay. Written a small code or a function where we have taken the training examples and created them using line space. It means that it is going to increase the value one step at a time. Okay, and we'll quickly run this. Don't try to go through this code. It is just the way we can plot the data. Now here you can see that when the model will or the graph will get generated, as and when the number of training examples. So with this, what we were doing is we were increasing the number of data points slowly, and with with time, as the number of training example increases, the test score and the training score actually will be similar. Okay, or rather it will be close. So we want to make sure, as we have talked in statistics, the more number of data points you have, the better the model would work. Okay. Now, the last thing which I want to show is how does the residual looks like. What is the residual? We all know residual is the difference between the predicted value and the absolute value. Okay. So all these points are actually the difference between the residual value and the predicted value. And we will quickly plot something with Okay, I'll quickly install Yellow Brick.
In the meantime, can you go up? The, this chart, can you explain again once?
Yeah, this one, right? So what I'm trying to say is, uh, see, our training score and the testing score, right? Just want to show one thing, that as and when the number of training example increases, okay, as and when the number of training example increases, your your score, or whether it's the R score in this instance, will be linear to each other. It means that if you increase the number of training examples to some extent, the result will ideally be consistent across the number of samples. Say for example, if I have less than 50 samples, your R square value could have been zero point 0.4, somewhere around 0.4, right? And if you increase this to say 80, it would be 0.65. And once it crosses that 150 mark, it is somewhat consistent across the number of data points. So if you see, there are instances where with the number of data point increasing, with the increasing number of data points, your score is actually getting bettered with each iteration, and there is still chance of getting a parallel line in this graph. You should add more number of data points just to make sure that you have reached that parallel with the training example.
Okay.
Right? So this actually helps us to figure out if the number of data points are quite good enough for our analysis or not. Okay. And as you know that when you train the data uh, with less number of point, it tries to overfit the model, because it doesn't have much reference about the data. So initially you will see that you have a very good accuracy of point. So obviously this is a training score. Okay, your training score is very good, but as and when you add more data to it, it gets it doesn't want to overfit the model, and with that your training accuracy actually decreases. So this is just a way to showcase that if your training accuracy actually decreases, it doesn't matter. It doesn't mean that your model is with each iteration your model is behaving differently and it is not working properly. It means that it is reaching a stable state where you have a, a good sweet spot between your low bias and your low variance. Okay, so Yellow Brick is downloaded. I will quickly okay, there might be a problem with this module. I will quickly check that. So this was just the way I just wanted to, okay, let me fix this. I think there is some mismatch with the packages. Okay, let me fix this. So through this lines of code, I just wanted to make sure that, we understand how, the residuals are organized. Okay, and what is the relationship between the residuals? As we have already seen in some of our slides, that the residuals are always normal distributed. Mm, Yeah, just wanted to show that the residuals are normally distributed, but I will fix this and share this document with you guys. But in any case, if someone is able to run this, I think there is some problem with the conflict of libraries, but that's okay. And then the last thing which I wanted to show is the prediction of the error plot. So this is the error plot, which you can see. This is the residuals which we have, and from here we are able to find the best fit line, which is the dashed line in dark. Okay, so you can use these type of codes to further perform EDA on top of any data set. Okay, next I will request you to go to this folder, right, our shared folder, and download the two files, linear housing data and one CSV file which I have uploaded. Once you're able to open this file, do let me know over the chat. The link is here. Are you able to open this file? Okay, great. Now let's do this together. What we have in the data set is, the data set is about the USA housing prices, as we have seen in Boston housing data set. What you have, the average area income, the average area of the house edge, the number of rooms, the number of bedrooms, the area population, uh, the price, and the address, right? And please import the file which is already there. So you can see the average house age and average house income and everything, right? Now you can look into the shape. You have 5,000 data points with 7 columns, right? And you can look into the data types as well. So some are float and some are object. Now the question is, perform the descriptive statistics on the data. How can we perform the descriptive statistics? Can someone tell me? df.describe. Okay, yes. So I will quickly do data.describe, right? It will give me the summary of the data or the descriptive statistics of the data, right? Okay, can you remove any missing value? How can we do that? If you have seen this file, you can probably remove some missing values. How can we do that? Drop NA. Okay, we can do through drop NA, but rather we can try something called data is null, right? Yes, Bhargav is right. So we have data dot is null, right? And then we will do a sum. We'll do a sum. Okay, nothing found. No problem. So if you have any values which are missing, you can just use this in order to perform our analysis. Now we need to perform EDA and find any correlation, right? How can we do that? We can create a heat map. df.core. Yes, you can do that. Not a problem. But I at times find, right, right. I'll quickly copy what Bhargav has pinged and we'll paste. So we will do a show. Right. So this is our correlation. This looks good. So we have certain variables which are, correlated, average income and price, but price is our target variable, no problem. So from this plot, what we can figure out is the average number of rooms and the bedroom, right, is 0.46. Right. So these are correlated. 0.46 is a little significant. So we can say they are correlated. Let's look into it in detail. So we will let's create a scatter plot with the number of rooms just to make sure that the correlation. So we'll do plt dot no, not scatter, it should be scatter. Right, we can do plt dot scatter, then our data frame, which is data, and then we have average area number of rooms, which we can, I'll just copy from here. Right. This is my data point, and from here I will plot it with the price, and then plt dot Okay, now this is my scatter plot. So yes, there is a linear relation. Why I am saying a linear relation? Because if you want to draw a line, I mean between, right? There is a linear relation, and let's do the same thing with, you know, the number of bedrooms. Hmm. So you can see the relation between the number of bedrooms and the price. Can someone tell me what is the inference you can get from these two plots? Is this a linear relation? No, right? This is not a linear relation. So from here, what we can say is that, you know, um, we can say the number of rooms, or rather first we take the number of bedrooms, has little or no effect on the house prices compared to the variable, which is the number of rooms, which seems to be linearly correlated. So this is linearly correlated because, you know, if a line passes through it, it is absolutely linearly correlated. Yes, if the number of bedroom increases, the price does not increases, right? Now, can we do some more analysis? Okay, I just want to do some EDA, okay, just so that you understand. Let's create a density plot. Data dot plot. Right, this is how I can create a density plot, and kind is equals to density subplot is equals to true. True. So we can make it better. We want to create some subplots. Please, I'll explain. Don't worry. size can be, let's try it, 30, 10. Okay, so just wanted to show you, the subplots of the data. Okay. So if I plot the data over a density function, you can see all of them are normally distributed. The average number of bedrooms has some peaks because obviously this is some sort of categorical value where you have 2 beds or you have 4 beds or you have 6 beds, but all of them are normally distributed. So for us, this works fine, right? So what I have done is I have created a density plot, right? And with that density plot, I have created the subplot of all these, different variables. And just to make sure that, previously there was one more graph was coming to picture, I've just make both of them false and just wanted to show you the subplot. Now once this is done, we can create our target variable. The target variable, for if I want to do a regression, I have to basically find the independent and the dependent variable. The dependent variable is price. How can we test all the assumption of linear regression before jumping to model? Yes, that is correct. So assumption wise, if you see all the plots which we have done here, right? The first assumption, if I go to the 4 assumptions, a linear relation between dependent and the independent variable. So just like we have, created a relationship between the dependent and the independent variable, you can create your own, scatter plot just to understand which of them are independent, which of them are linearly correlated, right? With um, with the target variable. So this is why I have shown you only one example. You can do this for the rest of the data set. Okay. Next is where you want to find if there is no multicollinearity between the independent variables. Okay. From you can find out the collinearity using the heat map, right? If there are a significant amount of collinearity, you have to basically drop some of the columns. But for our instance, there was no collinearity. So that is tested through this. If some assumptions fail, what measures should we take? Please discuss this. Yes, obviously we will discuss it. Now for our better understanding, this is just a simple data set which I have given you, because there are some few folks who don't understand, they come from a non-technical background. And if I go very fast with, how to drop, even before doing an ETA, that will be a little challenging. That is what we have faced earlier also. So if you understand this linear regression, I would say this might look a little, slow to you, but we'll make sure that all of these points which we are covering in the slides will be discussed. Don't worry about it. Okay. If we have, very, there is a collinearity in the data, we'll make sure we'll drop it. So I will also share you a data set for the bike sharing price model where you have to drop certain variables. Okay. Yeah. And you can see the residual homoscedastic. I have plotted this using one of the plots, but there was some issue. I will try to fix it so that you can also see there is homoscedasticity in the data, and there is no heteroscedasticity. Next is we will look into residuals are normally distributed in the same graph. If you would have not run it, you have seen the graph which shows you there was a normal distribution of the errors as well. Okay, so all these assumption will be taken care before we jump into the modeling part. So that is why we are doing EDA here. Okay, now once the subplot is created, we will create the target variable. Now, for instance, if I, can you tell me which columns can I drop and doesn't, make any sense for our prediction? Address. Okay. Right. So what we will do is, yes, we can copy it, no problem. I will quickly write 2 lines of code just to make sure that I just want to create a target variable. Okay. So two, you have to create two variables. One is the feature and one is the target, right? And in feature, what you want is, you don't want your price as well as your address, because price will go to your target variable. So I can just quickly write data drop, and then I can put the value as price and address. Right. And I want to delete it. So I can give it access equals to 1, right? And it will delete the values for you. And in target, I just want only one feature. So it will have only the price point. Okay. So this creates my feature and the target. If I just want to show you, feature is okay, no problem. And target is this. So you will have only one value, right? So your feature and your target is ready. And now you want to, standardize your data. So at times what will happen is, much of your data set is, uh, having a large scale. So if you want to minimize it, say for example, so why I'm telling you this is because we will require this in the subsequent, lectures. Is, for example, your data point is huge, say 10,000, and it ends somewhere around, say, yeah. Now you see the minimum and the maximum range is too much, right? It is going to be, it is going to vary a lot. So we want to create is, we want to shrink this data by taking a standardization. Okay. For example, if you just, for one example, if you just download, you know divide this by 100, right? So this gap will shrink, right? This gap will shrink. So this is how we do standardization. And for standardization, we can use something called the min max scale. So this is just for your knowledge purpose, because we will be using this heavily. um, let's import from sklearn preprocessing port min max. Right. And can we do something about it? Let's take a variable x is equals to min max underscore scale. and we'll pass on our feature. Okay, and before we move to the the regression part, what we need to do is we can do our data partition, right? And that's where I will use the code which was shared. Right. Right. I will use xtrain underscore xtest, ytrain ytest, and we will do a train test split x and y. Let's change this to say 3. Okay, just to make sure we are not using the same pattern, and change random state, whatever you want. And I might get an error, so I will just quickly import from scale it was model selection, right? So I will quickly pass on train test split, right? It says y is not defined. Oh, okay. Y is not here. It is target. Now your partition is created. Okay. Now can we analyze the metrics? Okay, we'll quickly go here. I'll copy all the libraries and paste it here. So we have sklearn.linear model linear regression, and okay, that's right. We have to fit our x train, right? And we have to fix our y train, x train and y train, right? And then we will predict on top of model. Just give the regression function as well. So g is equals to linear regression. Okay, can we calculate the R square score? So we can write from sklearn. If you want to copy, you can just copy it. But this is quite easy. sklearn.metrics, import to score, right? And from here I can just quickly print. Let's print the, for example, test, right? And you have your to score. Right, so this is your R square value. Let me see if I can do something with the scatter plot. Right, you can see a linear relation between the y test and the predicted value, and that's why you can see, the test result is 0.91. It means that, this follows a very good linear relation. This follows a very good linear relation. Now let's look into if there is anything in the residual. So residual, okay, I will plot a histogram. It is just to make you comfortable with the terms, okay? So don't worry if, if you're thinking that how will I remember these, metrics, how to import it. So that's not a problem. So this is all we will develop with habit. Okay. So I'm just creating a residual. This not residual is basically the observed minus predicted value. So I have predict, and can I create some bins? PLT dot show. Right. See, the residuals are also normally distributed. Okay. This is the residual. When you draw a line, right, all these residuals are normally distributed. Now, with that, we can say that, we can perform analysis on top of this data through a linear regression algorithm. And the last thing which we'll do in today's class is just to find the metrics. As I told you, I don't want to give you the prediction, the modeling part right now. It's just like um, want to make sure that you understand all the terms. What is root mean squared error? What is mean absolute error? Right? What is R square? What is variance and bias trade-off? Okay. And from the next class onwards, we will try to do a full end-to-end um, model where we will predict the results, and we can also find basis certain feature what will be the price of the house. Okay, so let's metrics. So I can do metrics dot, can copy it. So likewise, you can perform this for the other ones. You can just change this to mean squared value, right? And you can do it for np.sqrt, and then you will pass on the values here, right? And it gives you 1000842. So this is how we just calculated the root mean squared value, the mean absolute value, the r squared value, and this gives us a solid foundation of how to process the data in Python. In the next class, what we will learn about an end-to-end regression problem, how to perform analysis on a regression uh, uh, on a regression data set. And with that, we will also move on to something called the regularization, which will be rich and lasso. And we will complete this with a small Python tutorial on uh, gradient descent. So that will complete our entire linear regression process. Obviously, we'll go through a set of assignments as well, where you will be able to understand how linear regression is applied, and you have to answer a few questions.